Hello dear learners, welcome to the second video of the course Signals and System Analysis. In our previous video, we have seen the course overview, such as the course information, the course description, and the course schedule. So, in the course description section, we have seen that the course will have 6 chapters. From these 6 chapters, the first chapter is about classification of signals and systems. So we will subdivide this chapter 1 into 3 subsections. So the first subsection is about classification of signals, and the second subsection will be about basic continuous and discontinuous time signals. And the final subsection is about classification of systems. So let us see from the first subsection of this chapter, which is classification of signals. Before diving into the classification of signals, let us see first what signals are. So let us define signals first. So signal is a physical quantity. As you see here, a signal is a physical quantity that varies with respect to time or space or another independent variable and conveys an important information. So a signal will have an important information within it. So basically, in this course, we'll focus on signals which are time dependent. So time dependent signals will be covered in this course. So mathematically, we can represent signals as x of t for continuous time signals and as x of n for discrete time signals. So to be clear with what signals are, let us see some examples of signals. These are examples of signals. Here, examples of signals are listed. So the first example is electrical voltage, which is an electric voltage that is as an input for an RC circuit. See this circuit, for example. So here there is an input voltage V, which is given as an input for this circuit. So this is a time-dependent signal, a time-dependent voltage signal. So this is an example of signal. And also there are another examples of signals. Sound pressure wave, which is denoted as P of T. A digital image, a two-dimensional signal, which can be represented as Im of n. So this is a discrete time signal. Electrocardiogram waveform x of t, which is most commonly available from health centers. So this device is available from health centers, and the signal shown in the form of waveform can be denoted by x of t. So it can be taken as an example of a signal too. Another example of signal is a stock market price, P of n. So it is a discrete time signal. It is dependent on a discrete variable n. So it is a discrete time signal. So this is an example of a signal also. So these are examples of signals. So if you are required to list an examples of signal, you can use these examples. Also, there are also another examples. You can refer further from another notes. Thank you. Okay, let us start now on the classification of signals. So there are different classification of signals that will be covered in this course. The first and the basic classification is continuous time and discrete time signals. So bear in mind, this classification is very important. Continuous time signal, when we say continuous time signal, it is a signal that can be denoted by x of t, where t is all real values of t. So t will take all real values. So if a signal is represented in this form, we call it is a continuous time signal. In other words, a discrete time signal is a signal which can be represented by x of n. So where n takes any integer value. So it is a discrete value. Integer values are discrete values. So this signal is defined only at discrete points. So discrete values. That's why we call it a discrete signal. Actually, Most physical signals or real-world signals are continuous time signals, but for digital signal processing or for computer application of signals, it is necessary to convert these continuous time signals into discrete time signals by using a sampling technique. We'll see it further in the chapter 4. Let us see the key relationship between discrete time signals and continuous time signals. So continuous time signals, after sampling, they will become discrete time signals. So continuous time signals, as we noted previously, they are represented by using a variable x of t. So t will take all values of real number, while a discrete time signals are denoted by x of n, and n is an element of integer. The main difference between x of t and x of n, or continuous time and discrete time signals, are that continuous time signals are represented by using x of t, where this parenthesis is used. But for discrete time systems, we use square brackets instead of parentheses. We use these square brackets. So this is another difference between continuous time and discrete time signals in terms of their representation. An example of continuous time signal, voltage across a capacitor. And an example of discrete time signal, a sampled audio with frequency of 44,100 Hz. So it is a sampled continuous time signal. To analyze continuous time signals, we use these techniques: Fourier transform technique or Laplace transform techniques. While to analyze discrete time signals, we use these techniques: Z transform or discrete time Fourier transform. So if we say this about continuous and discrete time signals, let us go to the second classification of signals, which is analog versus digital signals. So let us see a little about this classification. Analog signals has continuously valued amplitude at each time instant. So the amplitude of analog signal is continuous valued. So digital signals takes values from finite or usually binary alphabet. So we can say that all continuous time signals are analog, but not vice versa. But discrete time signals may be either analog or digital. So discrete time signals cannot be always digital. Sometimes they are analog, and if they are given a finite value, they are categorized as digital signals. For example, a 16-bit audio can be classified as a digital signal as well as a discrete time signal. The third classification of signals and systems is energy and power signals. Please bring your attention here. Energy and power signal, it is the very important classification in signals and system analysis. You'll face so many problems related with this classification in signals and system analysis. So you should understand clearly this classification. So what does energy signal means and what does power signal means? So let us see each of them one by one. The energy signal E of a continuous time signal x of t over a finite time is defined by using this integral. Energy is equals to the integration of absolute value of x of t the whole square dt, where the integration goes from negative infinity to positive infinity. So if we get a finite value for this integral, we say this signal is an energy signal. So if this integration is finite, so the power will be by default 0. So another classification in this part is the average power, which is mathematically defined as P equals to a limit t approaches to infinity 1 over 2t, where this capital T is a period. the integration of absolute value of x of t the whole square dt, where the integration goes from minus t to t, minus t to positive t. So let us see a very important classification rules to classify whether a signal is an energy signal or a power signal after applying it with this integration. So we say a signal is energy signal if this condition is satisfied. That means the integration energy, the energy is finite. That means the value of E obtained by using the previous integration, this integration should be finite between 0 and infinity. And power is 0. So if this condition is satisfied, we say a signal is an energy signal. And we say a signal is a power signal if the value of P is greater than 0 and the value of energy is infinity. So if these conditions are satisfied, we say a signal is a power signal. Also note this important description here. Note that periodic signals are always power signals. Periodic signals. Trigonometric signals are periodic signals, cos of omega t plus theta, sine of omega t plus theta. So these like signals, these periodic signals are always categorized under power signals. While the finite duration signals are energy signals. So if a signal is a finite duration, for example, if you take exponential signals that decays exponentially and that have finite duration, they are classified under energy signals. So to make clear more about this classification, let us see an example. Energy versus power example. Classify x of t equals to a raised to minus 2t u of t as energy or power signal. Solution. So to classify this as energy or power signal, we'll use the above integration formula that we have mentioned, these integration formulas. So always I recommend to first compute the energy value because this integral is more clearer than this integration, this power integration. So we'll compute the energy value by using this integration formula. So substitute the value of x of t in the above integration formula. So E will be equals to, energy will be equals to the integration from negative infinity up to positive infinity, of this value. Since u of t exists unit step signal which is defined for only t is greater than 0, this integration will become into this form. So the interval will be from 0 up to infinity because u of t is defined only for t is greater than 0. For t is less than 0, u of t is 0, so 0 times the signal will be 0. So we'll consider this interval only. So after squaring e raised to minus tt, the whole square will get e raised to minus 4t. So the integration will become the integration from 0 up to infinity e raised to minus 4t dt. So after integrating, you will get this 1/4 joule, which is a finite value. So this indicates that the energy is in between 0 and infinity. So it is a finite value. Therefore, if energy E is a finite value, we can conclude that it is an energy signal. The given signal is an energy signal. So if you compute the power value, it will be 0 by default. So once if you obtain a finite energy signal, by default, you can conclude that the value of power is 0. You can prove it by substituting the values into the power integration formula. So in this way, we can classify whether a signal is an energy signal or a power signal. So the fourth classification is even and odd signals. Let us see this classification. A signal X of is even signal if the signal satisfies this condition, such as X of minus t is equals to X of t for all values of t. In other words, a signal X of t is an even signal if it is symmetric about the vertical axis. What about odd signal? A signal X of t is an odd signal if the signal X of t satisfies this condition, such that X of minus t is equals to minus of X of t for all values of t. Again, in other words, a signal X of t is an odd signal if it is antisymmetric about the vertical axis. So any signal X of t can be expressed as the sum of its odd part plus its even part. Its even part plus its odd part, where its even part can be expressed as half X of t plus X of minus t, and its odd part can be expressed as half X of t minus X of minus t. So we'll use these formulas to compute the even and odd components of a given signal. Again, let us see an example to clarify this classification. How to classify a signal into its odd and even components, or how to compute the odd and even components of a given signal. For example, this exponential signal is given. So let us compute its odd and even components. So we will substitute this value of X of t into this formula to find its even component. So X even of t equals to half X of t, which is e raised to t, plus X of minus t, which is e raised to minus t. And this exponential expression is equivalent with cos hyperbolic of t, or hyperbolic function of cosine of t. So this is from trigonometric identity. Again, its odd component can be computed by using this formula. So we substitute the value of X of t in this formula. Half X of t, which is e raised to t, minus X of minus t, which is e raised to minus t. So again, this is equivalent with sine hyperbolic of t, or hyperbolic function of sine of t. So in this way, we can compute the even and odd component of a given signal. The fifth classification of signals is periodic and aperiodic signals. A continuous time signal X of t is periodic with fundamental period t naught, which is greater than 0 if this condition is satisfied. X of t plus t naught equals to X of t, where t naught is a fundamental period for all t. So that means a given signal X of t repeats itself after t naught, after an interval t naught. If we obtain the fundamental period t naught, it is possible to compute the fundamental frequency simply by taking the reciprocal of the fundamental period, 1 over t naught hertz. And the angular frequency omega naught in terms of rad per second can be computed by using this formula, 2 times pi times f naught. So if t naught is given, we can find the fundamental frequency, we can find the fundamental angular frequency. A discrete time signal X of n is periodic with period n, where n is a positive integer if this condition is satisfied, such that X of small n plus capital N is equals to X of small n. So this discrete time signal is also repeating itself after a positive integer value n, where n is a fundamental period. So let us see examples of periodic and aperiodic signals by using graphical representation. You see, these are an examples of periodic signals. This is periodic signal because, as you see, this signal is repeating itself after a period t, you can see, you can observe from this graph. Similarly, for discrete time signals, this is an example of predict discrete time signal. As you see, also, this signal is repeating itself after a period n. So a signal is repeating itself after a period n, a positive integer value n. The last classification of signal is deterministic and non-deterministic signals. This is a clear definition. By seeing only the title, you can see what deterministic and deterministic signals are. Deterministic signals can be determined. They can be predicted. They can be mathematically expressed. This is the simple definition of deterministic signals. Behavior of these signals is predictable with respect to time. It is predictable. This is a key concept behind deterministic signals. They can be predicted. And also they can be mathematically expressed. This is an example of deterministic signal. For example, x of t equals to sine of 3t. This, a signal x of t can be represented by using mathematical expression. So we can conclude that it is a deterministic signals. While non-deterministic signals they are random signals. They cannot be predicted with respect to time. They cannot be expressed mathematically. They are uncertain. These signals cannot be expressed mathematically. For example, a thermal noise generated is non-deterministic signal. So we cannot predict its value. It is a random signal. It is uncertain signal. So we can conclude this type of random signals or uncertain signals, non-deterministic signals or unpredictable signals. So this is all about the classification of signals. If you have questions, suggestions, and comments, you are welcome on the comment section. Thank you.